Chapter 4 is about adding, subtracting, multiplying, dividing graphs. What happens when you take one graph and add it to another graph? What does it look like? How do you add graphs? What does that mean? So here we have two graphs on the same one. We've got function A, which is in red, and function B, which is in blue. Function A is how many people are enrolled in college. Function B is how many people are enrolled in university over the past few years. What they want us to do is on the same grid, we want to have a graph of the total post-secondary enrollment, and we'll do that in green. So in 2004, how many people were enrolled in university or in secondary enrollment, university or college? Approximately.
16.
Around 16 million, right? So maybe just. And then in 2005, more or less than 2004. A little bit more, right? Again, we could take the 6 and add it to about 10.5 and say maybe about 16.5. And then in 2006, a tiny bit more. And in 2007, looks like that would add up perfectly or very close to 17. So if we drew the lines in between, we've got one more year. And so we get an idea, this is what it means to add graphs. You take your red graph, you add it to your blue graph, and you get your green graph. What did we do? All we did when adding graphs is you're just adding the y values. One graph plus another graph to find out what that would equal to. All we're doing is adding our y values to see what it would look like. Part B. The stopping distance for a car is a function of the speed of the car when the brakes are applied, and they tell us this formula, that the stopping distance equals the reaction time distance and the braking distance. So what does that mean? Well, you want to stop. Let's say you're driving down the highway and a deer goes onto the road. Well, you say, oh, there's a deer on the road. What should I do? I should stop. So once you make that decision in your head that I should stop, there's going to take a slight moment of time for your foot to come off the gas, go onto the brake, and press it down as hard as you can. Okay? Now, if you had been driving on the highway at 1 kilometer an hour, I don't know if a car can go that slow. You're like, oh, there's a deer on the highway. You move your foot over and you slam on the brakes, and you probably have only traveled maybe 2 feet before you slam on your brakes and the car comes to a stop. Because in the time that it took you to react, because you're driving slow, you don't go very far in that reaction. But had you been driving, maybe you're in Germany and you're on the Autobahn, which has no speed limit, and you decided to go as fast as you could, and you're going 220 kilometers per hour, and a deer jumps on the road, and you're like, there's a deer, I should stop. By the time in the same amount of time as before that you moved your foot over and slammed on the brakes, because you're going so fast, you may have traveled 300 meters just in the moment of deciding to stop before you've even slammed on your brakes, and there is deer everywhere. So the faster you're going, we've got a blue line here. That's just the reaction time. And so what this blue line is telling us, here's our blue line, I'm going to underline reaction time distance there, is that if you're going 100 kilometers per hour and you say, I better stop, and you quickly slam on your brakes, by the time your brakes are actually applied, you've traveled 20 meters, according to this. Because it takes you some time to react, and in that time that you're reacting, you travel forward. This is your stopping distance in red. So they've given you this part of the formula in the red graph. How am I going to show my braking distance? Well, if the red graph is equal to a blue graph plus a green graph that you don't have, can you see that you could get, I'll color code it, green would be equal to does that make sense? Instead of rewriting all those words, if I moved reaction time over to this side, then I would get the red minus the blue is equal to the green. And again, we're going to figure out how long, so we're going to figure out what is the braking distance for these certain speeds. So if we take some points on this graph, and just looking at the graph, the 100 looks like the easiest point to start, because there is a point on the braking distance for 100, and there's a point on the stopping distance. So apparently you're going 100 kilometers per hour. According to this, if you see a deer and you slam on your brakes as quick as you can, you will still travel 90 meters before you actually completely stop. That includes the reaction time that it took you to slam on the brakes, plus whatever skidding that would happen when you slam on your brakes and come to a complete stop. If that's the case, if that deer was 90.1 meters away, they would be fine. So we have 90 meters. If the stopping distance was 720, that would mean that our braking distance here would be 70. So you slam on your brakes and you would slide, or the brakes would cut into place, and you would travel 70 meters while braking. Just sounds like quite a far distance. The other easy point on this graph is at 0. You are driving in your parked car. You're not traveling any speed whatsoever. A deer jumps out on the road in front of you. You're like, you slam on your brakes. And you stop exactly the same place you were stopped to begin with. So your braking distance at that point would also be 0. So again, for this one, all we have to do is subtract our y values. So we could take any other points here. It looks like we're at 58. Whoops, put that in blue. 58 minus 26. That would give you somewhere around 32. Take another point. Here we've got 20 minus 8. That would be somewhere around 12. And we get our green graph that would be in between those. And so the same thing that's happening with the stopping distance, the faster you're going, and it makes sense when you finally do apply your brakes, the faster you're going, the more distance you're going to travel before that car finally comes to a stop. So adding and subtracting, you're just looking at your y values. Nothing too crazy happens. Here we're just given two graphs. The y equals f of x, that is the graph in red, and y equals g of x, that is the graph in blue. And we're wondering what happens when you multiply these together. Where are things going to be? Well, when multiplying, again, all you're going to do, sort of the theme so far, is whatever you're doing with your two graphs, you're going to be doing that with your y values. Your x values are going to stay the same. So if you're going to be multiplying the y values and you've got two graphs, the first thing we want to determine are what are easy y values to multiply. Would you choose, would it be a good, this one where they intersect? That looks like it's about 2.583 multiplied by 1.76. Are those good y values to use? No, that mental math doesn't? Okay, good. Yeah, I don't think we'd want to choose those points because the mental math is not very easy to do. What would be some good points to choose? 0. 0 for either one, right? So if the red graph is 0, 0, right? 0 times anything will be 0. And if the blue graph is 0, anything times 0 is 0. So as far as drawing our new graph, we can look, here is where the red graph, well, and the blue graph is 0. That's going to be 0. Here's where the blue graph is 0. That's going to be 0. Okay? So any place where one of them is 0, it's going to be easy to multiply. What are some other easy things to multiply by? 1. So if either the red graph or the blue graph is 1, 1 times anything just keeps the other thing the same. So let's see here can you see that right here, the red graph is 1. So that means 1 times anything is going to stay the same. This point will end up staying the same. Here is one place where the blue graph is equal to 1. So even though the red graph at that point is not a nice number, it looks like it's at 1.5, 1.7, somewhere in there, I'm not sure. It's going to stay the same. So I can go straight up from where it's 1 here, and I know that that point is going to stay the same. Other than that, you can look and see if there's any other nice points. Like it sort of seems like right here, I've got a red value at 2, and when x is equal to 4, on my blue graph, it looks like it's equal to 8. So I could take that one, 2 times 8, and put a green point at 16. So what we do is we take a couple of y values. We make sure we look at where y is equal to 1, where y is equal to 0, because those are easy ones to do. But then we can take some other points as well and estimate them and sort of draw what we have. Now, a point that I didn't choose, but I'd like to do that right now, is this one right here. Because that's another point where the blue graph is equal to 1. So 1 times whatever the red graph is going to be what it's equal to. Where should I put the dot? Okay? I just have to go up and down from here until I hit the red graph, right? What's the problem? There's no red graph to hit. No matter where I go up or down from this, I never hit the red graph because the domain of the red graph was just when x was bigger than 0. And so there won't be any point that exists there. In fact, it says, what are the domains of f of x? Well, the domain of f of x was x bigger than or equal to 0. The domain of g of x was everything. But now the domain of them multiplied together, it only makes sense when both of them exist. So it's only x is bigger than or equal to 0. If we had to describe these graphs, would you say that the blue graph looks like a parabola? So another strategy that you'll sometimes use is just say, to get an idea of what the graphs are, is say, that looks like some sort of parabola. I'm just going to write x squared. What does the red graph look like? The red one? Close. What shape is this one? A square root, or an x to the half. So sometimes you'll have shapes that you know. Now what would happen if I took an x squared and I multiplied it by an x to the half? I would get an x to the, what's the rule when you multiply same bases? You get an x to the 5 halves. So apparently that's what that green graph is, approximately. An x to the 5 halves graph. But that doesn't fit with one of the ones we've done before. Kind of almost looks like part of an x cubed graph, like half of an x cubed graph. But it's not quite. And finally, the last thing we're going to look at is what happens when you divide two graphs. So you've got a red graph, which is f of x, and a blue graph, which is g of x, and you want to divide them. So just like before, we have to think about, if I'm dividing my y values, so we'll add that as our note again, because when you're dividing graphs, you're just taking your y values and dividing them. What are going to be important points for dividing? What are easy things to divide? Numbers, sorry? Even numbers. Yes, if the numbers are like nice numbers on here, we can do them. But what are some key things that, like when we taught multiplying by 0 was important. Multiplying by 1 was important. Can we have some similar things happen with dividing? What's going to happen with 0? What's going to happen with 0 on the red graph? What's going to happen with 0 on the blue graph? So there's one point where it's 0 on the red graph. That is right here. 0 divided by something is always 0. So that's easy. If the top graph is 0, then 0 divided by, doesn't matter what the other graph is, it's going to be 0. What about where the blue graphs are 0? Those become 0. Something divided by 0, 5 divided by 0 is 0? Undefined, right? That's not allowed. That's our non-permissible value. What did we do in our graphing unit when we had a non-permissible value? It either became a whole or an asymptote. Now, since we can't tell here if these things simplify, we're going to draw asymptotes for now. Sometimes you might start with an asymptote, and when you actually divide the numbers, you realize, ooh, it looks like there's going to be a hole there instead. So we're going to have an asymptote at x equals 3 and x equals, or sorry, negative 3 and x equals positive 3. So we've got a little bit of an idea so far of what's happening. Anything else for dividing that you would know? Okay, dividing by 1. So if you're dividing by 1, that's not going to affect the other number. So if we look on this graph, where's the blue graph equal to 1? That would be here and here, right? And so at those points, when you divide by 1, the other graph, it's not going to change. So our green graph would be through this point and through that point. What happens when the red and the blue graph are the same? It's going to equal to 1. So if we find out the intersection points, can you see that they intersect at this point, oops, this point there and this point there? At those points, we can go straight down and we know that our green graph is going to be equal to 1. Now, if there's any points that have nice numbers, like we said before, like for example, can you see that this is a nice number for a red graph and it's a nice number for a blue graph? The red graph is 1, the blue graph is 8. 1 divided by 8 would be 1/8. Not really a nice number for our green graph, but you could plot that as well. And I think we have enough points in our middle section to say this, that our graph is going to look like this. Yes? Yes, we still have to, if they exist. So now, what's going to happen in the other section? And this is another thing about dividing. Can you see in both of these other sections, when x is bigger than 3 and when x is less than -3, that your red graph is positive and your blue graph is negative? Positive divided by negative? It'll be negative. So we'll find out that this section has to always stay negative.